So, um, so in this video, we're going to talk about shape and interpolation, or what's often referred to as shape functions or interpolation functions within finite elements. So we're going to talk about it for the shape and interpolation function within a bar element. So when we first defined our bar element, we defined it to be a linear function of x, u of x, where we had two unknown constants, a is naught and a1. Okay, so um, at the nodes of um, our system, we would have two displacements that are known: u of I and u of j. Okay, so and they would be equal to those unknown constants a naught plus a1 times the location x of I. Okay, so x of I is in the global coordinate system. All right. So now the one thing I will mention here is that the length of the element would be equal to xj minus xi. So using these equations, these two equations here, we can rearrange them to solve for our two unknown constants, a naught and a1. Okay, so if we plug in what we get for a naught and a1, we end up getting this equation for u of x. Okay, so we have a constant a naught and another constant a1. Okay, so we can um, we can now rearrange this equation instead of being in terms of x, but we're going to rearrange it in terms of our two displacements ui and uj. All right, so um, so what we end up getting is we get two functions. We get ni of x and nj of x. Okay, so these two functions are called shape functions. Okay, which determine the displacement within an element. Okay, so we can define our displacement u of x as being the sum of nix times ui plus the sum of nj of x times u of j. All right, um, so we can then use the definition of strain, which says that the partial derivative of u of x with respect to x will give us our strain within our element. So if we do that, we can take the derivative of these two shape functions with respect to x to get this matrix here. So we take the derivative with respect to x, we end up getting um, -1 and 1 over LE for our derivative. If we take out the derivative of our shape function is often referred to by the capital letter B, and we can then, if we take out the 1 over length e term, we end up getting this value here for our this equation here for our strain within our element. And then the next thing is we can use Hooke's law to then calculate the stress in the element. So all we need to do is to just multiply the stress by the strain by the elastic modulus to get our stress within our element. Okay, so the important thing to note here is that we're talking, in this specific case, we're talking about the bar element or the truss element, which is the simplest type of element. So your shape functions, depending on the type of finite element that you picked, like if it's a beam element or a frame element or like a quadrilateral element, they will have their own shape functions that can be used to determine the stress and strain with the element, but they all follow a similar process in terms of taking the known values of your strain and then calculating, the known values of the displacement you determined from your global stiffness matrix, and then you can then calculate the stresses and strains using those known displacements that you solved for in the original problem.